In this video, I'm going to explain Euler's theorem from number theory. Euler was a mathematician in the 1700s, and he had many theorems, so this is just one of them, and you can find it often in a first course in number theory. So what it says is you have n to be a positive integer, and take any number a that's relatively prime to n. In other words, the GCD of a and n is 1. Then, if you take that number a and raise it to a certain power, phi of n, which I'll explain in a second, you'll get a number that's congruent to 1 mod n. In other words, a number that's 1 more than a multiple of n. Now, what is this phi of n? Well, it's called the Euler phi function or totient function. And one definition is that it's the order of the group Zn cross. In other words, that's the number of positive integers relatively prime to n and less than n. Now, a special case of this theorem is a theorem we've seen before called Fermat's little theorem. And this is the case where n is chosen to be a prime number, call it p. And then this phi of n, it's a little bit easier to see what phi of p is when p is prime. It's simply p minus 1. Why? Because zp cross is 1, 2, 3 all the way up to p minus 1. So there's p minus 1 elements. And so this term here, the size of this group Zn cross is p minus 1. If n is not a prime, phi of n is not in general n minus 1. It's more complicated. On the next slide, I'll give a formula for phi of n. But anyway, then Euler's theorem says a to the p minus 1 is congruent to 1 mod p, not 0 mod p. In other words, a is not divisible by p. Here's an example with specific numbers. Let's take n to be 12, so that's not prime, and a to be a number 5. So 5 is relatively prime to 12. In other words, has no common factors with 12, so we can apply Euler's theorem. So Z12 cross is these 4 numbers. I just went through the numbers 1 through 12 and canceled or crossed out any ones that had a common factor with 12. These are the ones that are left over. They have no common factor with 12. And so this set has 4 elements, and so phi of 12 is equal to 4. Then Euler's theorem says that 5 to the 4th is congruent or equivalent to 1 mod 12. I could replace this a with actually 7, 11, 13, 17, anything that doesn't have a common factor with 12. Okay, so just as a check, 5 to the 4th is 625, and so Euler's theorem is saying 625 is 1 more than a multiple of 12, so that means 624 should be a multiple of 12. And then on the calculator, I did 624 divided by 12 and got an integer. In this case, it happens to be 52. Okay, now that we've understood what Euler's theorem says, let's turn to its proof. And probably the easiest proof uses results from group theory, namely Lagrange's theorem and so forth. So let's take this element G in our just general group. I'm just reviewing some group theory. We've got a finite group G, and we have an element G, and then R be its order. So what that means is G to the R is the identity element, and R is the smallest such positive integer. And we've seen before that this order R divides the order of the group. Why is that? That's because the subgroup generated by G, written here, just all the powers of G, and then when you hit G to the R, you're going to get back to the identity. This is a subgroup of size R, whatever the order of G is, and because it's a subgroup, Lagrange's theorem says that its size has to divide the order of the group G, and its size is R, so this implies that R divides G. Okay, so the order of any element divides the order of G. That's what we've explained so far. And so say R times S is equal to the order of G for some integer S. Basically, S is equal to the order of G divided by R. So starting from this fact that G to the R is equal to E, raising both sides of this equation to the s power, we get g to the r times s is equal to e to the s. Now e to the s is just the identity element, and so since r times s is the order of g, we get g to the order of the group is the identity element. Okay, so this was just all pure group theory. This is a general fact that in any group, any finite group, if you take an element of the group and raise it, or in other words, apply the group operation to it, the order of g copies of lowercase g, multiply it together, you'll get back the identity element. Okay, so now we just apply this result to the group G, that's z mod n times, and the element, the number A is congruent to some, or equal to some element G in z mod n times, and this is where this condition that A and n had to have GCD equal to 1, that way A is identified with an element of this group, and the order of this group is denoted by phi of n. That's what the definition of phi of n was. The identity element in this group is just the number 1, or 1 mod n, and so what this equation turns into is simply A to this order of G turns into phi of n, and this E turns into 1 mod n. And so that's it. That's exactly what Euler's theorem says. Now, for Euler's theorem to be useful, we need a formula for phi of n. And here's one formula which I won't prove. It says to find phi of n, what you do is take n and multiply it by the following. You run through the primes dividing n and multiply by p minus 1 over p. Let's do an example. So phi of 12, we take 12 and multiply it by, well, we have to find out the primes dividing 12. I factor out 12 and see that the primes are 2 and 3. So when p is equal to 2, I get this factor p minus 1 over p becomes 1/2. When p is equal to 3, this factor becomes 3 minus 1, which is 2, over 3. Then I multiply all this together and I get 4. So note that even though the prime 2 is repeated in the factorization, here I only account or apply, it appears only once. Okay, and to check, well, z mod 12 cross is these numbers, 1, 5, 7, and 11, and indeed there's only 4 of them, and so that's this formula works or checks out in that case. Okay, so for the example I'm going to do below, we need to compute phi of 100. So phi of 100 is 100 times, and then we have to figure out the prime factors of 100. Well, we factor out 100, it's 2 squared times 5 squared, so the primes we need to look at are 2 and 5. When the prime p is equal to 2, the factor is 1/2. When the prime p is 5, the factor is 4/5. Again, just 1 less than the prime is the numerator, and then the prime is the denominator. Okay, and then when you multiply all this together, you get 40. Now, here's a fun problem that I've seen in high school math competitions, for example. It says find by hand, so without a calculator, the last 2 digits of some number, like 19 to the 84 power. And so this is a number with 108 digits. And so you can't just type it in the calculator. The calculator, it might not be able to handle this number. Although Sage is, and we'll calculate this in Sage. But anyway, we need to find this by hand. Okay. And so the solution is, well, first of all, realize that the question is asking to find 19 to the 84th power mod 100. That's one key idea, that because the last 2 digits of a number are that number mod 100. In other words, the remainder when you divide by 100, those are the last 2 digits of that number. Okay, so Euler's theorem says that 19 to the 40, here's where this computation that phi of 100 is 40 comes in, is congruent to 1 mod 100. So once we have 19 to some power is 1 mod 100, that enables us to easily calculate higher powers of that number. So for example, if I just square both sides of this equation, or congruence, I get 19 to the 40 squared is congruent to 1 squared mod 100. This 100 does not get squared. It's just one of the rules for modular arithmetic. Okay, so then 40 times 2 is 80, so 19 to the 80 is congruent to 1 mod 100. And we need, so 80 is close to 84, which is what we want. So split 84 up into 19 to the 80 times 19 to the 4, using the rules of exponents, that the exponents add. And so since 19 to the 80 is just 1 mod 100, that's what we've calculated here. What we really need to find is 19 to the 4th power mod 100. So we reduce the problem from calculating 19 to the 84th, which is an impossibly huge number, to 19 to the 4th, which we can do by hand. And that's what I've done on the next slide. So I need to find 19 to the 4th. Well, 19 squared, let's get started with that. So then I just do the multiplication, and it turns out to be 361. So I just need to take it mod 100 again, so I can forget about the 3. So 19 squared is 61 mod 100. And I'm after 19 to the 4th, so raise both sides of this equation, or congruence, to the power 2. And so I get 19 to the 4th is 61 squared. And then just to show you I actually did this by hand, we get this. And so the 3721, I take it mod 100, and that's 21. And so 19 to the 4th is 21 mod 100. And so that's our answer, 21. And to show you or check this, that Sage can do this, I did 19 to the 84th, and it's a huge number, but indeed the last 2 digits are 21. So this is just an interesting problem, kind of a fun, cute problem using Euler's theorem.